Okay, we're now going to begin the second part of the 1D flow lecture series. We haven't actually talked about flow yet. We just set up the stage. Basically, we set the stage up for now understanding how to calculate flow parameters, etc. So the idea is that the reason why we want to, the main reason, let's say, of why we want to understand how flow or how water flows through soil, particularly water, is because we have clearly many cases in the field, probably all cases, where water has to flow through the soil, and so we have to basically make sure that we know how to handle that process and how to quantify it and calculate the relevant parameters. Now, sometimes we have to know the rate at which, or with the, let's say, the ability of the soil to conduct water, because sometimes we have situations where we want to restrict the flow, or sometimes we want to improve the flow or enhance the flow through the soil. Okay, the case of restriction is the case of a dam. Clearly, if we build a dam that is made of soil, we would like for the water to have a hard time going through that dam, because we would like to retain the water behind the dam, right? On the other hand, there are some cases where we would like the water to drain, to flow through the soil, to seep, right? Remember, seepage is the flow of fluids through soil. So we would like the water to have to be able to efficiently and quickly flow through a soil mass. Okay, in that case, that would be the case of drainage systems, for example, behind a retaining wall. So to quantify the ability of soil to conduct water, we need to essentially conduct lab tests. Okay, sometimes we can do them in the field as well, but typically we do this in the lab. The person that first started this type of studies was a guy by the name of Darcy. Okay, and in the 1850s, he decided that there was a need to determine or to calculate or to study the way in which water flowed through soil. So what we have here is an illustration of Darcy's experiment, which is actually the experiment that we use today in the lab, the type of experiment that we use today in the lab to determine the relevant parameter, which is called the permeability. It's this little k here, which we'll get in just a second. Okay? We actually talked about that parameter before. If you go back to the lecture series where we classified soil, we said that the fines content of a soil controls this parameter. Okay, but we didn't really talk much about the actual parameter itself, which is the reason why we're talking about it here. So let's begin with the experiment so that we can understand what's going on in that experiment. Here we have a soil specimen. Okay, so the soil is brought to the lab, let's say, and is placed inside a cylinder, a tube. Okay, at the boundaries of this cylinder or tube, there is a cap, okay, in each boundary, and there is a mesh. Okay, so the soil grains are prevented from going into, let's say, out of the tube. Okay, now the end cap is connected to a tube. This line here is a tube, smooth tube that is connected to a reservoir of water. Okay, and on the other side, there is another tube that is connected to another reservoir. Okay, now what Darcy did, and this is usually what we do in the lab, is he built something like this. Okay, and he said, okay, I'm going to add water here. I'm going to add water. Okay, so that the elevation of water in this reservoir is always kept constant. Okay, so he continuously adds water so that the elevation here is always at that level. That is the water table, sorry, is always at that level. And over here, clearly, if you can, if you know, from intuition, you can realize that if water is added to this reservoir, the water is going to go through the tube, through the soil, and out into this reservoir, and from this reservoir it will overflow, right? The water is not going to flow from this location up, because we are going to calculate and prove that that cannot happen. But just if you think intuitively, water is not going to flow upwards unless there is some added energy, right? Input, like a pump or something. There's no pump here, it's all gravity based. So Darcy adds water here continuously, keeping this constant. And this water level remains constant because the water, any extra water that passes through overflows. And this is going out of the system. Okay, now we'll leave this at this point looking like this because we're going to get back to this. Now, let's say that this is the datum. Okay, the datum. Now, again, you may say, well, why didn't you choose the bottom of the slide as a datum? Well, we can choose the bottom of the slide if you want. But let's choose something that is closer, just so that we can keep the figure kind of more proper. Okay? So again, the selection of the datum will not change the ultimate answer that we're going to get. Alright, so then Darcy said, okay, I'm going to kind of quantify or describe the flow system here. So he said, okay, first thing first, selection of the datum. Second, let's take a point, that's point number 1, and let's take point number 2 here. Okay? Now, why did Darcy select 2 points? Because when we think of flow, we have to think of flow from one point to another point. We cannot just think of flow as some kind of random thing that goes from somewhere to some other place. I mean, we have to think of a point and 2 points, meaning that flow occurs from one point to the other point. Okay, that's the engineering approach. So here's point 1, here's point 2. What is the elevation head at point 1? Well, before we talk about heads, why do you choose point 1 and point 2 here and here? Well, Darcy said, I'd like to know what happens in terms of flow from a point, from the beginning of the soil specimen to the end, because I want to concentrate on the flow through the soil, not through the tubes or coming out here and like a waterfall, whatever. I want to concentrate on the flow between these 2 points because I want to concentrate on the flow across the specimen. Okay, so now we can say that we have our 2 points and we're going to determine the heads at those points so that we can determine the total head difference between the points, the delta H. So, what is the elevation head at point 1? The elevation head at point 1 is that distance from the datum to the point. Datum to the point. What is the pressure head at this point? Well, if you were actually scuba diving inside this tube, what is the pressure that you would feel? Well, that pressure would be associated to that distance, the distance from that level, from that water table, all the way to you, which you are inside the tube there scuba diving. So, pressure head is from the point to the water table. Okay? Now, because this is soil, we can neglect the velocity head like we said before, and we get that the total head at point 1 is the distance from the datum to the top. Okay? Alright. Let's go to point number 2. Point number 2 is on the other side of the specimen, so we are now associating the point with what happens here. This is the elevation head, and the pressure head is the distance from this point to the water table. Okay, which is that. From the point to the water table. Okay, that distance. That is the pressure head. That is the elevation head at point 2. And therefore, the total head, this is kind of messy, but I think that you can actually see this, is from the datum to the water table. Just like on this side. Total head at point 2. Okay? the difference in head, in total head, is that distance h1 minus h2. Okay? And that is what drives the flow. Now, we said that delta H drives the flow in the previous, in part 1 of this lecture series. And maybe you were left like, okay, you know, you were left thinking, what does that mean, like drives the flow? Well, think about it. Let's say that you raise this water, this reservoir very high up, maybe like up here or something. What do you expect will happen with the flow intensity or the flux, the flow rate? That is how much water is going to pass through the system per given time or per second, let's say. Well, there's going to be a more intense flow, higher flow rate if you increase this all the way to here and leave this one there, right? Because the difference is higher. That's what I mean by, or that's what we mean when we say that delta H drives the flow. The larger the delta H, the larger the Q, the flow rate through the system, which comes into play in the calculation of this K. Okay, now, here's the situation. This specimen has a length L. Okay? That is the length of the specimen. The specimen also has a cross-sectional area. The area is pi r squared, right? Where r is the radius. So the cross-sectional area of flow, A, L. Those are the dimensions of the specimen. Okay? Now, what Darcy did is the following. He essentially set this up, determined the H2 and the H1, determined the delta H. Remember, these are all determined because you can imagine that this is sitting there on a desk on top of a lab. Okay, sorry, on top of a desk in a lab. Okay? So this is known, delta H, because it is imposed by Darcy, right? He decided he wanted this reservoir here and this one here. He could have decided to put it up here, but he decided to put it here. So delta H is imposed by the experimentalist, in this case Darcy in the 1850s. Okay? The specimen size is a given. You can measure it. You have it in the lab, or Darcy has it in the lab, let's say, and it has an area. So that's given. So A and L. Now, I'd like you to focus your attention on the water that is coming out here and overflowing from this reservoir. What Darcy did was he took a cylinder and he collected the water, okay? And he timed with a, probably not with a stopwatch, but with a kind of probably old school type of stopwatch with needles and with gears and all that. He timed he timed how long it took for a given volume of water to be collected. Okay, so for example, 1 cubic centimeter per second, something like that, right? That is a measure of Q, flow rate. Okay, this is volume per unit time. So the units could be something like centimeter cube per second, cc per second, for example. That is what he measures here. Okay, so he measures the amount of water that comes out per given time, and he determines the flow rate. So then what he did was the following. He said, okay, I'm going to plot the results of many experiments. So he creates a plot. Here he has a compilation of the parameters that he knows. He knows delta H because he imposed it. He knows the area because he selected the size of the specimen. And he knows the length of the specimen. So he says, I'm going to put down here A times the ratio delta H over L. I'm just going to write that down there. Okay? That quantifies my system, my setup. In the y-axis, I'm going to write down or plot the flow rate that I get for a given scenario. Okay? So, this is what he does. This right here is 0, right? 0, 0. So, if delta H is 0, then the water levels are at the same location. That means there's no flow. So the flow rate is 0. Okay? So that point is already known even before he starts doing the experiments. In the next experiment, he sets up the system just like this. Okay? He puts this one up here, this reservoir, he puts this one here, and then he starts the flow. He continues to add water here, this water overflows and he measures. And he measures this Q. Okay? Clearly, the delta H is some value, L is some value, A is some value, so he has some value for that ratio or this compilation of parameters. He has that value for that system, and he measures this Q. Okay? Then he says, all right, keeping the same soil, I'm going to raise this up a little bit so that it's here. What does that do? Well, A is constant, L is constant, delta H now is larger because H1 is now from here to here. Datum to the elevation, new elevation of the reservoir. So the delta H is larger, therefore this ratio or this compilation becomes larger, right? And then he measures the Q for that system, the system where the reservoir, the inlet reservoir is here. And he gets a higher Q. And then he does it again. Right? What does he do again? Well, he raises this even higher. Right? And he measures that corresponds to this this factor here, because delta H is now even higher. So this goes up, and the measurement, what he measures, Q, which is what he measures, it's actually bigger, okay, or larger. As we had said before, remember, if we raise this up, then the flow rate increases, and that's what he gets. And then there's a point where if he raises it too much, then the increase in flow rate that he gets is actually lower, so the data actually looks like this. Make a point in writing here that each of these points is an experiment, one experiment, okay? And the difference between each point is the setup. Each point corresponds to a setup where the location of this water reservoir is higher than the other ones, okay? Than the previous one. Clearly, you could say, well, I don't have to change this reservoir, I could actually lower this one. And that would make the same, it would do the same thing. You would get the same type of trend, because what you're doing is just increasing delta H by separating the distance between these two, okay? Or separating them and increasing the distance between them, because the distance between them is actually delta H. Okay, so then he says, this is great. There is a relationship between what I impose, my setup, okay, and the flow rate that I measure for a given soil. This is for one soil. Remember, we didn't change the soil. Okay? And then he says, okay, I'm going to draw a straight line through the data at the initial portion of the curve, and the slope is going to be called K. Okay? And K is what we call the hydraulic conductivity. And you'll see it in the next slide. This is the parameter for a soil that describes how able, or the ability of soil to conduct, of that soil to conduct water. Okay? Clearly, that's the case if we run Darcy's experiment with water. But if we run Darcy's experiment with oil, for example, like petroleum, okay, people in petroleum geomechanics run this test, but using petroleum. In that case, it would be the petroleum conductivity, the one we measure. Okay? Now that we're talking about that, actually, let's raise a question here. Do you think the the conductivity, the K measured for oil, let's say petroleum conductivity, would be the same as that for water? If you were to run a set of tests for petroleum, would you get the same curve? Well, the answer is no. and press, if you press pause and think about it, then come back, then you'll realize that clearly if you have a fluid here that is very viscous, okay, let's say perhaps you have never seen petroleum, but you have seen, I don't know, honey, okay, so if you have honey, the honey is going to flow very slowly because it's very viscous, okay, so what you'll get is something that looks like this. That would be the data that you get for honey, okay. So the conductivity K that you measure depends on the fluid as well as the soil. Okay. Now, this K that you measure is the K, the hydraulic conductivity in the case of water, for the soil that you have in here. That parameter is one of the most important parameters. Personally, I believe it is the most important parameter in geotechnical engineering for this description of a soil. Okay? And we can get into that later on. You'll see the relevance of the permeability, sorry, the hydraulic conductivity later on. Now another question arises. Well, what is this break here? Why does it not continue to go straight? That is the data. Why is it that if we raise this very high and increase the delta H, the difference in flow rate is not as high as when we raise it just a little bit, let's say, along this range here? The reason, if you press pause, you should think about it actually and not just listen. You should stop and then now think about it. Okay, now I hope that you have some answer. I cannot ask you what the answer is because I cannot talk to you. But if you think, or if you thought of inertia versus viscous drag, then you were correct. So what happens is that beyond this point, the delta H is so high relative to the other parameters. This is not delta H alone, this is delta H over L times A. That parameter, which is that conglomeration of parameters here, is so high that there is a change in the flow regime. So the fluid starts flowing in the turbulent regime. So the flow becomes turbulent beyond this point. When this parameter is low, the flow is laminar, which is typically the case of soil, okay? And when this parameter is high, then we have turbulent flow, in which case the conductivity is dependent on this, okay? Because you can see the slope changes at every increment of this parameter. So generally we are concerned with, in soil mechanics, in geotech, we're concerned with the laminar regime. That's why we adopt the K that is associated to the initial portion of the curve.